Hello, my name is Jumanon, and this is the summary of the chapter 5, uh, a survey of optical gas sensors for harsh environments. There are 8 titles. First, introduction. Importance of gas detection, enhanced sensitivity and selectivity in gas sensors can improve efficiency and reduce costs in energy and automotive industries by enabling real-time monitoring of combustion emissions to meet environmental regulations. Sen- Sensing technologies. Various gas sensing methods include electrochemical, optical sensors, acoustic sensors, and photonic crystal-based sensors. Electrochemical sensors like SNO2-based ones are popular for hydrogen and CO detection due to their reactivity to oxygen changes in metal oxides. Optical gas sensoring. Optical sensors are promising for long-term stability and multiplexing capabilities. Examples include fiber rack gratings coated with Paladin for H2 detection, and AU nano particle-coated optical fibers that detect H2 and CO and can also measure temperature. Material innovations. Research groups use materials like YSA-AZO, NB-doped TiNO, and combinations like NiO, SiO2 for H2, and CO detection. Selectivity is a focus, with some materials showing sensitivity to specific gases in mixed environments, charges and future directions, humidity, temperature, dependence, and high cost are challenges. Future improvements may include miniaturization, distributed networks, and multiplex sensors arrays to enable broader applications in high temperature and mixed gas environments. The second title, uh, localized surveys, plasmon resonance theory and background. Advantages of metal oxides for high temperature sensing. Metal oxide sensors are stable at high temperatures, are resistant to chemical poisoning, making them ideal for high temperature applications. Their sensing mechanism relies on absorption or desorption of oxygen ions or reversible chemical reactions on their surface. Selection of metal oxides. Active metal oxides are more sensitive for high temperature sensing compared to inert ones. Mixed metal oxides like CNO, SNO2 offer improved sensitivity and selectivity by facilitating easy charge transfer. Nano composites in sensing combining plasmonically active nanoparticles with metal oxides enhances sensitivity and stability. These composites stabilize nanoparticle mature and dimensions at high temperatures, enabling their performance in harsh environments. Nanoparticle plasmonic ammonics, ammonics. Gold and silver are commonly used for plasmonic sensoring due to their optical properties. Gold is preferred for high temperature stability, while silver offers benefits but has oxidation charges above 500. Potential applications, these high temperature stable nanocomposites show promise for monitoring emissions in extreme environments, such as turbines in aircraft and power plants at temperatures of 500 or higher. And the third title, uh, sensoring reactions and predicting sensory performance with metal oxide plasmonic nanocomposites. The equation where the subscripts GNS denotes gas and surface respectively, and the term S denotes an absorbed oxygen atom. It is also expected and confirmed through experiments such as Alice allipometry that the charge donation to the absorbing oxygen occurs preferentially from the metal nanoparticle compared to the metal oxide, as there would have been a shift towards shorter wavelengths of the plasmon peak due to a reduction in the refractive index of the metal oxides. If the absorbing oxygen extracts the electrons from the metal oxide preferentially instead of the metal nanoparticles, as opposed to the ex, experimentally observed shift towards longer wavelengths on oxygen exposure, similar to the reactions of oxygen reactions of any adsorptase with such nanocomposites can be explained in terms of charge transfer mechanisms. And the fourth title, terminal energy harvesting. And this two image is about gas exposure results from air H2 mixture waste. Terminal imaging data on left and white slide data on right. And this is about gas exposure results from air. There are three cycles separated by dashed lines of CO concentrations to 5, 10, 50, 100 ppm. Gas on and off times are 40 minutes for both experiments. And you can see compare the three grouped images. This is about different experiments. The difference is the concentrations. And this is the calibration plot for H2, NO2, and zero analyze gases in an air background from terminal image and white light image data. And fifth title, NIR terminal energy harvesting. And this terminal image exposure done with visible light absorbing sample left. Terminal imaging exposure done with near infrared absorbing sample right. And sixth title, Principal common analysis. Uh, the two images file terminal image for spectral PCA on left and B terminal image in reduced wavelengths spectral PCA on right. The steps title multipolar resonance. Peak position versus time plot comparing responses of different resonance to hydrogen in air. Concentrations were 200, 500, 1000, 5000, and 10,000 ppm H2 in air, and B calibration curves showing sensitivities of results in A. The last title conclusions. Thermal energy harvesting in both the visible light and NR regions allow elimination of the white light source, which means a reduction in sensor complexity and one less component that can break or need maintenance. Results have been shown that demonstrate sensitivity, ppm level, detection of H2, CO, and NO2 analyzed gases. PCA results have been shown that show similar gas selectivity within significantly less information. Terminal energy harvesting combined with full and reduced wavelength PCA allow the overall sensor package to be greatly simplified and miniaturized. Additionally, multipolar resonances have been shown to result in an additional probe of gas environment. Okay, that's all. Thank you.